Okay, so in this lesson, we're going to discuss partial fractions. Now, the point behind this lesson is to end up decomposing rational expressions into the sum of partial fractions, which are the fractions that you add and reduce to the same denominator in order to obtain the given rational expressions. Now, if I were to recall a bit what a rational expression is, a rational expression is a quotient of two polynomials. Okay, so for example, I have here x minus 1 over x plus 1 into x minus 2. Now the numerator and denominator both consist of polynomials, therefore this is a rational expression. So we're first going to start with proper rational expressions. Now what is proper rational expressions? Now, as I said, rational expressions are quotients of two polynomials. Now, whenever the degree of the polynomial at the numerator is smaller than the degree of the polynomial at the denominator, in that case, you'd be dealing with a proper rational expression. Okay, so we're going to start with decomposing into partial fractions the rational expressions that are proper. So let's just first start by looking at the rational expression we have in this example here. Okay, so we have x minus 5 over x plus 1 into x minus 2. Now, if you think about it logically for a second, at the denominator I have x plus 1 as a factor and x minus 2 as another factor. How could I, when I reduce to the same denominator, how could I end up having this product at the denominator? You would basically tell me it's by adding a fraction, whatever the numerator is, with x plus 1 at the denominator, with another fraction with x minus 2 at the denominator. So when you reduce to the same denominator for these two fractions, when you're adding them, you end up with the denominator that we have in our rational expression, right? It makes perfect sense. So now we need to determine what the numerators are in order to have successively decomposed this rational expression into the sum of its partial fractions. So if we observe again this rational expression given, as we said, it is proper. Its numerator is smaller, has a degree smaller than the degree of the denominator. So whenever you're decomposing it into partial fractions, the partial fractions cannot possibly be improper. Improper as the numerator has a bigger degree than that of the denominator. So logically, since the original rational expression is proper, then the partial fraction that compose it have to be proper as well. Okay, so over here, x plus 1 is linear. It has a degree equals to 1. Similarly for x minus 2. So since these two partial fractions are proper, then the numerator must have a degree smaller than the degree of the denominator. Then the numerator must have a degree strictly smaller than 1. Now degrees are natural numbers, so strictly smaller than 1, that leaves us with a degree equals to 0. And polynomials with degrees equals to 0 are in fact constants. So the numerator in this case is a constant, and for the other fraction is also constant since its denominator is linear. So now I have two partial fractions with the linear factors at the denominator and with constant numerators to be determined. Okay, so let's just reset all of this and now start solving the example. So over here, we just agreed that this rational expression is in fact split into the sum of these two partial fractions. Okay, so the easiest method to find a and b is to start by reducing to the same denominator on the right hand side, which leads us at the numerator to a into x minus 2 plus b into x plus 1. So expanding at the numerator and grouping similar terms together, the denominator remains unchanged. So for the terms in x, when you expand, I'm going to expand and group immediately. So I have ax plus bx, which leaves me with a plus b into x, when the two terms are grouped together, and with constant term of negative 2a plus b. Okay, so now these two fractions being equal and having the same denominator, then their numerators must be equal. So their numerators consist of equal polynomials. So the coefficients of similar terms are equal. So over here, a plus b must be equals to 1, and negative 2a plus b must be equals to negative 5, because here we're equating these numerators to be equal, so their similar terms have equal coefficients. So regarding this system of simultaneous equations, you can use your calculator to determine the values of a and b, or you can solve it algebraically using any method you're familiar with. So using your calculator, you end up with a equals to 2 and b equals to negative 1. So therefore, if we call the expression given f of x, so then f of x is in fact the sum of 2 over x plus 1 minus 1 over x minus 2. So this is f of x decomposed into the sum of two partial fractions. Now if we move on to the next example, so you'd notice at the denominator, again, we have this factor to be linear. So its corresponding partial fraction must have a constant at the numerator as agreed in the previous example. However, regarding the second term, I have a linear factor to the power of 2. So over here, we need to determine what are the possible partial fractions that when you add, give you x minus 1 all squared into x plus 2 at the denominator. Okay, so one possibility would be adding a fraction, whatever its numerator is, with x minus 1 all squared at the denominator, with a fraction, whatever the numerator is, with x plus 2 at the denominator. Now, this is a sum that would lead to the common denominator we want, x minus 1 all squared into x plus 2. But is it the only possibility? No, because over here x minus 1 is raised to the power of 2, and we know that whenever we're finding the least common denominator with common factors involved, the least common denominator would in fact include the highest exponents. So there is a possibility that I could have added a fraction with x minus 1 all squared and another one with x minus 1, and then add the third one with x plus 2, whatever the numerators are. So the common denominator here is also x minus 1 all squared, because again, I repeat that whenever you're considering the least common denominator, you would basically end up taking for common factors the highest exponents for the least common denominator. So x minus 1 all squared and x minus 1 are both represented by x minus 1 all squared in the common denominator, because x minus 1, in fact, you can multiply both numerator and denominator by x minus 1 in order to reach x minus 1 all squared. So the rule comes as follows. Whenever you have a linear factor to the power of n, the possible partial fractions would be basically the linear factor to the power of n added to the fractions with the same factor with all the exponents all the way down to 0. And for example, if you have a fraction with x minus 1 all cubed multiplied by whatever other factor, then x minus 1 all cubed would be represented by the partial fractions corresponding to x minus 1 all cubed, x minus 1 all squared, x minus 1. So all the way to, sorry, I previously said all the way to 0. It's all the way to 1, okay? Because 0, x minus 1 to the 0 is a constant, okay? So whenever you have it, if you have it to the power of 4, then the first partial fraction would be x minus 1 to the 4, the second one x minus 1 cubed, the third one x minus 1 squared, and the last one x minus 1, because these factors have x minus 1 to the 4 as a common factor. Now, of course, the decomposition does not necessarily have all of them. For example, over here, I could end up having 0 at the numerator here, and then eliminating this fraction from the sum. But I cannot assume at the beginning that the fraction is not there. There could be a possibility that the numerator is, in fact, different than 0. So this is why we consider the general case, and then if any of the fractions is not present in the sum, its numerator would end up canceling out as a 0. Okay, so let's just go back now for the time being to solving the example, having said all that. So over here, and by the way, since the factor that is being squared or raised to any exponent is linear, the numerators of the partial fractions would still consist of constants. So it's a over x minus 1 all squared plus b over x minus 1, and then we move on to the second factor to c over x plus 2. So over here, what I need to do is determine a, b, and c in order to get to the decomposition of the partial fractions. So again, the same method we've used in the previous example. We start by reducing to the same denominator. The same denominator, which is x minus 1 all squared into x plus 2. That's the least common denominator. So a would end up being multiplied by x plus 2, b by x minus 1 and x minus 2, and c by x minus 1 all squared. So over here, I'm going to expand and group similar terms immediately. Of course, you are not required to do that in order to avoid calculation mistakes. But over here, we have terms in x squared, which are bx squared and cx squared if we were to expand. So it's b plus c all squared. Then the terms in x, we have an a from the first term, a 2 minus 1, so that's a 1b from the second term, and a negative 2x c, so that's minus 2c from the third term. While for the constants, we have 2a minus 2b plus c. That if we basically were to expand and group similar terms. So these being equal, having the same denominator, then the numerators are equal again. So the coefficient of x squared is negative 2. The coefficient of x is 9, and the constant term is 5. So setting up the system, now this is a system 3 by 3, which you can end up solving on your calculator. So a plus b minus 2c is 9, and 2a minus 2b plus c equals to 5. So using your calculator, you determine a equals to 4, b equals to 1/3, and c equals to negative 7 over 3. Then if I were to call this f of x, so then eventually f of x is 4 over x minus 1 all squared plus, now over here b is a fraction. Now do not put the fraction at the denominator, simplify it, because a fraction at the numerator is not really in simplest form. So the 1 would remain at the numerator and the 3 would drop down to the denominator. So it's 1 over 3 into x minus 1 minus 7 over 3 into x plus 2. The third factor is x plus 2. Yes. So this is f of x decomposed into the sum of 3 partial fractions. Now if we move on to this example, again we have this to be linear, so its corresponding partial fraction has a constant at the numerator. Well, if we look at the second one is quadratic. Now again we go back to the original rule that says that the partial fractions in this case are proper, because the rational expression we're dealing with is proper. So over here I have an x squared plus 1 at the denominator, which has a degree equals to 2. So this partial fraction being proper, the degree of its numerator is strictly smaller than the degree of the denominator. The degree of the denominator is 2, therefore the numerator has a degree strictly smaller than 2. Strictly smaller than 2, then it could be 0 or 1. So if it's 0, then the numerator is constant, while if it's 1, then the numerator is linear. So for that reason, since I don't know whether it's constant or linear, it could end up being either one of them. So for that reason, I end up considering, as for the numerator, the one with the highest possible degree, which is linear. So the numerator here is in the form ax plus b. Now, you're going to tell me or ask me, what if the numerator is constant? Why are we assuming that it's linear? Because if the numerator is constant, then we could end up having a equals to 0 and eliminating the term in x. So we'll only be left with b. But if you consider from the beginning that the numerator is constant, if the numerator turns out to be linear, the constant would not lead you to the linear factor, but the linear factor could possibly lead you into constant if the numerator is a constant. So for that reason, we always consider the highest degree, the highest possible degree for the numerator. So briefly, in case you are dealing with a factor that is also cubic, for example, if I had x cubed plus 1 multiplying x plus 3, then the corresponding partial fraction for x cubed plus 1, since this is a degree equals to 3, then the numerator has a degree strictly smaller than 3, which could be 0 or 1 or 2. So we always consider the highest possible degree, which is ax squared plus bx plus c. And similarly, if this factor was to be squared, in this case, we'd consider this one squared plus x cubed plus 1 to the power of 1, again with a quadratic numerator. So whatever whatever the factor inside the power is, we always consider the numerator having a degree strictly smaller than the degree of that factor. Okay, and if we have a factor with an exponent greater than 1, then for the partial fractions, we consider all the partial fractions with the denominators, including all the factors or the exponents all the way down to 1. Similarly to what we did in the previous example. So now let's just work on solving this exercise. So over here we have, as agreed, sorry, let's just call it ax plus b over x squared plus 1 added to a constant divided by x plus 3. So reducing to the same denominator would lead to x squared plus 1 into x plus 3 at the denominator, and at the numerator we'd have ax plus b into x plus 3 plus a into x squared plus 1. So expanding and grouping similar terms, so for the terms in x squared, from the first term we have an ax squared. I'm sorry, here I used a again. We cannot use the same variable twice. So this is a c. Similarly, this has to be a c here. So over here it's a x squared plus c x squared. Then for the term in x, we have 3ax to bx from the first term, which is 3a plus b. No x from the third term, so it's 3a plus b for x. And for the constants, we have 3b from the first term and c from the second term. So over here, equating the numerators of these two fractions, since they have the same denominator, then a plus c is 2, 3a plus b is 6, and 3b plus c, the constant, is negative 1. So consequently, we obtain this system of equations: a plus c equals to 2, 3a plus b equals to 6, and 3b plus c equals to negative 1. Then a is 21 over 10 using your calculator to solve the system. B would be negative 3 over 10, and C would be negative 1 over 10. Then if I were to call this expression f of x, then f of x would be 21x minus 3 over 10 into x squared plus 1 minus 1 over 10 into what was the last factor, x plus 3. So these are the partial fractions corresponding to the given rational expression f of x. Now in this last example, we're going to look into improper rational expressions. So a rational expression is improper if the degree of the numerator is equal or greater than the degree of the denominator. So before you start setting up the partial fractions, always make sure if the given rational expression is proper or improper. If it's proper, you can immediately end up writing the sum of the partial fractions. If it's improper, you have to, in fact, divide first and then use the remainder of the division divided by the divisor and decompose that into partial fractions. I'm going to tell you basically what that consists of. So you'd notice here at the numerator I have a degree equals to 2, and the denominator I have a degree equals to 2, so that's an improper fraction. So being improper and knowing that partial fractions are proper. So the sum of proper fractions cannot lead to an improper fraction. So this is why, in order to get rid of this improper expression, what I need to do is start by dividing 2x squared plus 1 by the denominator. If I expand the denominator, I would end up with x squared minus 1. So I start by dividing the numerator by the denominator. So long division, 2x squared divided by x squared, first term divided by first term. That gives me a 2, because 2x squared over x squared is 2. Then what I would do is multiply 2 into each factor of the divisor. So it's 2x squared minus 2. Then what we would do here is subtract, but don't forget this negative expands into the whole polynomial. So 2x squared minus 2x squared cancels out. Now the negative x I have here has no common or similar term down there. So it just drops down. So it's negative x. Well, 1 minus 2, it becomes 1 plus 2, which gives a 3. Now we'd notice that the degree here is 1. The divisor has a degree equals to 2. So consequently, we can no longer divide. We can keep the long division going as long as the number or the factor we have here has a degree equal or greater to the degree of our divisor. When the degree here becomes smaller, that means that that is our remainder. Okay, so now, in fact, if I were to call this f of x, how would I write f of x? Now, f of x is, in fact, the quotient 2 plus the remainder, negative x plus 3, divided by the divisor. So f of x, which is 2x squared minus x plus 1 divided by x squared minus 1, is our quotient plus the remainder over the divisor. Okay, so over here, if I were to add a page here, so f of x is 2 plus negative x plus 3 over x squared minus 1, which again is x minus 1 into x plus 1. Now, this expression here, the remainder over the divisor, now that's proper. So that can be decomposed into partial fractions. So I consider this separately. You can work with all f of x, including the quotient. But I do not recommend it. I'd rather you take the remainder over the divisor separately, because the expression and the calculations would be much simpler, and decompose that into partial fractions and then put them back in f of x. So x minus 1 is linear, so its numerator is a constant. Similarly to x plus 1, it's linear, so the numerator is constant. So I reduce to the same denominator, which is a into x plus 1 plus b into x minus 1 divided by x minus 1 into x plus 1. So here, expanding and grouping similar terms. So I'd have a plus b into x, that comes from ax plus bx. So, and a minus b Okay, so that leaves me with the following system. A plus b equals to negative 1, and a minus b is equals to 3. So using your calculator, that leaves me with a equals to 1 and b equals to -2. So then it's 2. So f of x is 2 plus a is 1, so it's 1 over x minus 1. A had x minus 1 at the denominator, yeah. Minus 2 over x plus 1. So that is f of x decomposed into the sum of its partial fractions.